In this video, we will learn about organic reactions that involve free radical intermediates. So to start off, we should define what free radicals are. And free radicals are molecules that have unpaired electrons. And generally, because these electrons are unpaired, then these molecules are very reactive. So before we get into the actual reactions, we should think a little bit about the stability of these radicals. There are various features that can stabilize free radicals, much like how we thought about various features stabilizing positive or negative charge in an organic molecule. One thermodynamic stabilization that can take place is that of conjugation. So being one bond away from a pi bond allows for the free radical to be a little bit stabilized because we can draw in resonance forms that look like this. And you'll note that I'm using an arrow that has a single head on it to indicate that only one electron is being shown as being associated with that arrow. And that would get us to the resonance form that looks like so. A second factor that can stabilize radicals is the degree of substitution on that carbon where the radical is located. So the more substituted the carbon atom, the more stabilized a radical at that position will be. The explanation for this goes into hyperconjugation concepts, where neighboring CH bonds can delocalize a little bit with the half-filled free radical orbital. A third factor that can stabilize free radicals is when there is a lone pair adjacent to the free radical. So for example, here in this methoxyethane here, there is a free radical on a carbon, and then one bond away from it there is an oxygen atom with its lone pairs there. And the reason that this is stabilizing is because we can imagine resonance that looks like that, getting us to a resonance form where there's a carbon-oxygen double bond. And so I had indicated that these were different situations that lead to thermodynamic stabilization. And so what I mean is that this is saying that the inherent energy of the free radical is lower than it would be without those sources of stabilization. On the other hand, we can also think about radicals as being kinetically stabilized. So maybe these radicals are very reactive, they're very unstable, but they're not able to react because of the way the molecule is. And so for radicals specifically, the term persistent is used. So there are many free radicals that are found to be persistent, so they should be reactive because they're very high in energy, but they're not able to react most of the time because we're using sterics to kind of block all the potential pathways of reactivity. An example of a persistent radical is this one here. This is a molecule called TEMPO. It's a very useful free radical that's often used in medical imaging. I think it may help to think about this idea of thermodynamic stabilization versus kinetic stabilization by just looking at how TEMPO might hypothetically react with something to make a product, and then looking at the analogous free radical without the methyl groups on the side and undergoing the same hypothetical reaction. So if we were to look at the energy diagram for this, what we would expect is that for the gray free radical species here, you would expect some type of a reaction that looks like this in your reaction coordinate diagram. And for TEMPO, you'd expect that the free radical should be initially at about the same energy as a reactant as the one down here in gray. And so if that's the case, both reactions should start at the same point. The difference is that if the free radical in TEMPO is going to react, the colliding molecules, and the colliding reactants rather, will need to navigate around these four methyl groups that are around the free radical. And because of that, then our transition state energy is a bit higher. There's a larger activation energy. And because of that, then it's harder for TEMPO to get to the products side of this hypothetical reaction because, again, of the kinetic barriers. So a molecule in this state would be thermodynamically unstable because it would be able to react, but it's kinetically stable because it's unable to come over this barrier. This idea of thermodynamics and kinetics becomes more and more important when looking at various different reactions because in many different cases we have what are very unstable species, but just because they're unstable doesn't mean that they react, because we need to be able to also cross over that energy barrier to complete a reaction. To be able to perform any sort of organic radical reaction, we need to first be able to make the organic radicals. Most of the time in the organic reactions that we'll think about, These radicals are formed by homolytic bond cleavage. In other words, the bond between two atoms is split, with one electron going to one atom of the bond and the other electron going to the other atom of the bond, like so. Getting you to something that looks like this. This is different from the typical ionic reaction that is seen in organic chemistry, and that is considered a heterolytic bond cleavage. Again, just to contrast how these arrows look, this would be something like that, where we would indicate the pair of electrons is going from being shared between the two atoms to only being located on the nitrogen atom in this example. Now you can imagine that this type of process is not just happening all the time. It's not spontaneously the case that we like to break up a paired set of electrons. And it's also not the case that we like to reduce the amount of sharing that electrons experience between atoms. A question that should come up is that, well, given a bond, how can I possibly know whether or not it's able to undergo homolytic bond cleavage? And one way we can estimate this possibility is to look at bond dissociation energies. And we, in the past, have probably seen bond dissociation energies as a way just to talk about bond strength. It turns out that these bond strengths are defined as this process right here. So the amount of energy it takes to break apart a bond homolytically, not heterolytically. And so that's important to keep in mind because these numbers are a little bit more useful for thinking about radical reactions than they are for thinking about ionic reactions. So here are some typical BDEs. So a carbon-hydrogen is a pretty strong bond in that sense. It's hard to break that apart homolytically. Same for carbon-carbon. But as we start to incorporate halogens in there, so carbon, bromine, carbon, iodine, those tend to be weaker bonds, and these are definitely easy to cleave homolytically. And finally, another important one is the oxygen-oxygen single bond. That's a very weak bond. It's only 34 kilocalories per mole, so this is starting to venture into almost non-covalent territory. The reason that oxygen-oxygen single bonds are weak is because there's an antibonding contribution. This antibonding contribution kind of looks like what you see if you look at the paramagnetic oxygen molecule. There's two electrons in antibonding orbitals for the MOs of a molecule of O2. Analogously, the same thing is going on here, so this is a bit of a weaker bond. Despite that, it's still more stable to have a bond than to not have a bond, right? We still need to put in energy to homolytically cleave any of these bonds. And the way this is done is by either using the addition of heat or light. And so all of these radical reactions will have, importantly in their reaction conditions, either a component of heat or light. So let me just show you really quick what this looks like for a peroxide species. So this is something common that is used in radical reactions. Something like this, it's very easy to break apart. So we have that weak oxygen-oxygen single bond. Just heating this up a little bit will then break this apart into two of those free radical species. Before we get into actual specific reactions, it's useful to understand that there's really only three types of mechanistic steps that are involved in free radical reactions. We'll look at these three types of mechanistic steps in the context of the radical hydrobromination reaction, which involves overall the addition of HBr to an alkene. This is different from the normal Markovnikov addition of HBr to an alkene because we're now using light and we're inducing radical conditions. And what you see is that under radical conditions, the same reagent reacts in a different way, following a radical mechanism, to give you the anti-Markovnikov product. So the first step in any reaction involving free radicals is that we need to initiate or create the radical species. This is called the initiation step. Almost always this is going to happen through the incorporation of some sort of an initiator reagent into the reaction mixture. In the radical hydrobromination that I show as the example, that is the molecule AIBN on the bottom here. This is a very common initiator that's used. And its structure is right here. And looking at this, you might say, well, I don't see any weak oxygen-oxygen bonds or any weak carbon-halogen bonds. The reason that AIBN is a really good initiator is because this carbon-nitrogen bond here and the analogous one on the other side is actually really weak. It has a very low bond dissociation energy because if we homolytically cleave that, what we can do is we can actually create a molecule of N2 gas in addition to 2 free radical species. So that would look like so. So the driving force for this reaction then is the formation of N2 gas. Once that happens, then this initiator has initiated the radicals, and what we think of is we think of the unpaired electron as kind of reacting onwards in the reaction. This would then take place in the next step, which is called the propagation step. In this case, the radical is basically transferred between atoms and between molecules. So let's look at how propagation takes place in radical hydrobromination. Once we have our carbon radical that's formed by the initiation step, that radical can then react with an HBr molecule to create what we know is a relatively stable carbon-hydrogen bond and release a bromine radical. That bromine radical now is then the reactive species that's present in the reaction mixture. That can then go ahead and react with the alkene, and it'll do that like so. I'm going to show it like this, where I'm trying to show that a carbon-bromine bond is being formed, and at the same time I'm putting a radical on the more substituted carbon of the alkene. Once you get to that intermediate, then what you can do is, to get to product, do the free radical reaction between another molecule of HBr and this carbon radical, generating the CH bond we need in our product, in addition to actually making a new bromine radical that can then continue reacting with another molecule of cyclohexene here, and so on and so forth. And so when we talk about propagation steps, we really are thinking that this radical is kind of just jumping around. It's propagating through to other atoms, to another atom, to another atom, to another atom, so on and so forth. And this can happen for 10,000 steps or something. When we draw a mechanism, we're only going to draw what we need to show the formation of product, but we just want to keep in mind that in reality, it's not so simple. Right? This unpaired electron is really just kind of going all over the place. Another term that's used often when it comes to propagation is this term called abstraction. And abstraction is kind of taking the other view. So propagation is thinking of the electron moving on and living on continuously. Abstraction is talking about the atom that is reacting with the free radical. And so the way this works is I would say that this radical abstracts a hydrogen from HBr. Same thing I would say out here. This radical abstracts a hydrogen from HBr. So that's a H abstraction reaction. They all mean the same thing. You're just going to see both types of terms depending on the resources you look at. These abstractions or propagations will go on for many number of times, many different cycles, until eventually they will encounter what's called a termination step. In a termination step, what happens is we go from having a free radical to not having a free radical. So this could happen, for example, like so. As these reactions are proceeding, maybe one of the bromine radicals happens to run into a second bromine radical, and then, of course, the formation of a bond there would be overall a downhill reaction, lowering in energy and making bromine. And so then what we think of is that the lifetime of these radicals has ended because they've become paired again. It's important to understand that termination can happen a lot of different ways. So, for example, I could even have the initiator, the AIBN fragment, that radical reacting with bromine radical to make now an alkyl radical. That could be a termination step. And so in every radical reaction, there's all sorts of small amounts of byproducts formed from terminations that aren't related to the overall product that you're trying to get. It's not something you should draw out in all your mechanisms, but just something to keep in mind. Now that we have those mechanistic steps in mind, let's look at some different types of free radical reactions and what they do specifically. So the one we just looked at was radical hydrobromination, and as I alluded to, this reaction adds the bromine to the less substituted carbon, so kind of in this anti-Markovnikov way, and that's because we are trying to form the intermediate with the more stable free radical in it. Right? So when we have the addition of the bromine radical to the alkene, we have a choice of whether we want that resulting carbon radical to be on a tertiary carbon or a secondary carbon. since the tertiary one is more stable, that's the one that's going to be a lower energy barrier process, and that's the one that's going to happen more often. This should be our major product. You can actually also halogenate, specifically brominate and chlorinate, alkanes under these types of radical conditions. So just to give you an example, if I just take propane, react it with bromine, Br2, under the presence of light, that's able to generate this molecule 2-bromopropane in 97% yield. So now let's look at a mechanism for this process. Again, all of these radical mechanisms will follow the same process of initiation of some sort, propagation of some number of steps, and finally, termination of some sort. Here, we don't really have much to initiate with. We have propane and bromine, so definitely the Br-Br bond is the weak bond here. And so our initiation should happen like that. With a little bit of light energy, we're going to form the 2 bromine radicals. One comment I should make here is that you'll notice that I only draw the free radical electron. I'm not showing the remaining lone pairs that are on bromine. That's something just to keep in mind, that even though I haven't shown the other electrons, there are lone pairs here on the bromine still. So once we have our initiation step, then we should be able to do a propagation step. And in that propagation step, what's normally happening is that we're abstracting an atom from another molecule. And in this case, the only other option is to abstract that hydrogen from propane. That's where our reaction is happening. And so what I'm thinking of is the bromine radical pairing up with one of the electrons between the carbon and hydrogen, and then leaving the other carbon-hydrogen electron behind. That gets us to a molecule of HBr and the propyl radical here. This can then continue to propagate, in this case abstracting bromine from Br2. Same way, in the end making the product 2-bromopropane and another bromine radical. This is another thing that we'll see a lot during free radical mechanisms. The kind of initial species that you make, the bromine radical here, is made again at the end so that it can kind of continue propagating through. And so your mechanism could end here. We've already shown how the product is formed, and we could just kind of leave this bromine radical as is. But just want to point out that it's also valid to draw this same mechanism, but to use termination to form the product rather than another abstraction or propagation step. So let's say I am at this stage right here. So I'm going to pull that down here. Rather than reacting with a Br2 molecule, that carbon radical could instead just terminate by reacting with a bromine radical and form the carbon-bromine bond that you need in the product, and then that would be the end of the day for this type of a process. So again, we don't know necessarily which one of these pathways is taking place to make the product. They're both probably happening. So if we're given a molecule of 2-bromopropane, we can never say for sure whether it was formed using the upper propagation pathway or the lower termination pathway. So both of these are definitely possible. In general, we'll want to draw our mechanisms using the propagation pathway. The reason for this is that normally in a free radical reaction, what we have is a very low concentration of radicals. Right? Those are the reactive species. So a little bit of that is made, and then that kind of just reacts through. We don't have 1 molar equivalent of bromine radical floating around at all times. So basically what I'm saying is that this collision is a less probable occurrence than this one up here, and so it's a little bit more accurate to draw our mechanisms this way. Take a little bit of time here on these alkane halogenation reactions to look at something that applies to a lot of different chemical reactions, but is nicely illustrated by this specific type of reaction. So it turns out if you look at alkane bromination and compare it to alkane chlorination, bromination is a much more selective process. So previously I'd shown you that 2-bromopropane was formed at 97% yield. Well, it turns out the other 3% is the formation of 1-bromopropane. If you do that same reaction with chlorine gas instead of bromine, what you end up getting is a 55 to 45 mixture of 2-chloropropane to 1-chloropropane. Now, the theoretical yield is not actually 50-50 if there was no selectivity, because there's only 2 hydrogens in the middle to react and 6 on the outside. But whatever the case is behind the math there, the point is that the bromination is a much more selective process. It's choosing the less common hydrogen in position to react at, and it's doing it at a much higher ratio than you would see for chlorination. So why is that? It turns out that if you look at the H abstraction step, that is enough to explain the selectivity difference. Right? So let's look at here that abstraction step. So what I'm referring to is the step where the halogen radical is abstracting a hydrogen to form the carbon radical. Right? So in one case we have to form the secondary radical, the other case we have to form the primary radical. And the reaction is analogous for the chlorination. What's happening here is that on paper these look like very similar reactions, but actually these are different because the bromine radical abstracting a hydrogen, that's an endothermic process, while the chlorine radical abstracting a hydrogen, that's an exothermic process. And so what that means is, in part, that maybe the chlorine radical itself is very high in energy versus a bromine radical. And so the reactant energy is only one part of the whole thing. The product energy also matters if we're thinking about exothermic and endothermic processes. And so it turns out that if you look at HBr, its bond dissociation energy is 87 kilocalories per mole, while if you look at HCl, its bond dissociation energy is over 100 kilocalories per mole. And so what that means is an HCl bond is much more stable or lower in energy. Right? It takes much more energy to break it apart, so it is lower in energy. And so using all this information, what we'll do now is to look at reaction coordinate diagrams and to use Hammond postulate thinking to try to understand why all of this leads to a differing outcome of the two reactions. If you don't know what Hammond postulate says, it tells us that the transition state for any reaction from reactants to products is going to look more similar to the side of the reaction that it is closer in energy to. It is also going to be on the x-axis located closer to the side of the reaction that it is closer in energy to. So let's say I look at the two reactions for the bromine radical abstracting hydrogen. So I have the one in red here showing the abstraction to form a secondary radical. So in both cases I'm making an HBr. That HBr molecule and the free radicals summed up are going to give me the energy of my reaction process. So the HBr is consistent between in the red and the blue, but the difference is the stability of the free radical that's formed. So in the red process here, I should get a lower energy set of products compared to the blue process there. And hopefully it makes sense that since we're starting with the same two reactants, we are going to start at the same place. So then that lets me fill in the blue curve, which shows me the hypothetical reaction coordinate diagram for the formation of the primary radical. And so using the Hammond postulate then, I should see that, well, I'm going up in energy. That means my transition state, which is somewhere up here, is going to be closer to the products than to the reactants. Therefore, the structure here is going to look more like the products, and it's going to be located more to the right here. So this kind of the peak here is going to be more to the right on my reaction coordinate diagram. Overall, what that tells me is that this transition state will look like, in the blue case, a primary radical, and in the red case, like a secondary radical. So then I should have this difference in energy. The blue transition state should be higher in energy because it looks like the primary radical, which is less stable. Can do the exact same analysis for the other reaction that involves chlorination. Same idea. The difference now is that we're going overall downhill in energy because it's exothermic. And so we're starting at the same place, same two reactants, and we're forming two different products where the primary radical is again less stable than the secondary radical. And so that means that the blue curve should end higher than the red curve. But because my starting point is closer to the transition state, that means the transition state is going to look like my starting point, my starting reactants, and it's also going to be more on the left of my reaction coordinate diagram. What that means is that my transition state is just going to look like the reactants, and the reactants are the same in both of these reactions. So then the difference here should be very small. And so if you have a propane molecule and a chlorine radical, it should have a hard time distinguishing between these two barriers. So it's kind of 50-50 going over one or the other. Whereas for the bromine abstraction of hydrogen, then there's a much bigger barrier on one side, a much smaller one on the other, and that's enough to make the difference. So this is an example of a selective process, and this would be a non-selective process. Another way you'll hear this explained is that we have a late transition state in the bromination reaction, while for chlorination we're dealing with a early transition state relative to reactants or products. To give you an idea of how significant of an energy difference here it takes, the delta here between the two transition states is about 3 kilocalories per mole in bromination, and it's about 1 kilocalorie per mole in the chlorination. So it's actually not a very big difference, but that's enough to go from not selective to very selective. Let's end by looking at a few more free radical reactions. The next one is the allylic or benzylic halogenation. This is an interesting reaction because it seems at odds with the direct addition to an alkene we saw before. But it turns out that if you conduct your radical halogenation carefully, in a way that the HX concentration is very low, then you can actually get the halogenation to take place not at the alkene itself, but at a carbon that's at the allylic or benzylic position. So here this is the allylic position, and here this is the benzylic position. The way this is done is to use this set of reagents, which are called N-halosuccinamides, so either N-bromosuccinamide here, or N-chlorosuccinamide, NBS and NCS. So let's look at this mechanism. So the first part of this that we'll just kind of understand or assume is that the NBS and NCS are a source of a very low concentration of bromine or chlorine. So the vast majority of the reagent is going to look like this, and a small percentage of it is in equilibrium with Br2. The way this happens, it turns out, is that there's always just some contaminating HBr that's present whenever you buy the NBS or NCS, and this impurity turns out to be really important because it is enabling this equilibrium that gets to the very low concentration of Br2 that's needed for the actual reaction. So our initiation is happening the way it always happens. We have our bromine initiating into 2 bromine radicals. The bromine radical can then react with an alkene, but in this case it's abstracting a hydrogen now from the cyclohexene, getting us to the allylic radical, which is stabilized by conjugation here. This can then do an abstraction of bromine from Br2. That gets us to the allylically brominated cyclohexene here, and another bromine radical that can keep reacting. So again, this is very similar to the radical hydrobromination reaction, right? The same intermediates. We have a bromine radical and an alkene-containing molecule. And so you should ask, well, why doesn't it do that? And the answer is, well, it does do that reaction as well. So I'm going to do that in blue here. I'm going to have, let's say, the bromine radical coming in. It's going to attack, I guess, this upper carbon, the way I drew the product, like so. That can get you to this species here. Well, if that happens, then you should get an entirely different product of this reaction. So why does allylic bromination work so well? Reactions like this tend to go in 90+% yields. It turns out that, well, for the reaction here to continue going, kind of do the completion of the addition to an alkene, we would need to abstract a hydrogen from a molecule of HBr. Well, the whole point of setting up our reaction conditions this way was to minimize the amount of HBr present, which means that the next forward process here that we would need can't happen. And so even if this blue mechanism takes place and we make any amount of this alkyl radical, it's just going to sit there. Maybe a tiny percent of it is going to terminate, but most of it is not going to do much. And so because this is an equilibrium, that's kind of a single molecule process here, that red arrow is going to happen, and it turns out to be a majority of the time, favoring the bromine radical here, and that kind of makes sense because we have bromine radical instead of carbon radical. And so even if we get the wrong type of addition to alkene, that eventually still goes back to the reacting intermediates here that can then go on to actual product, where this is actually our stable end point. All right, 2 more reactions here involving a tributyl hydride reagent. So tributyl hydride is often written this way, so Bu3SNH. This is a very useful reagent for reducing CX bonds into CH bonds. So essentially removing halogens, replacing them with hydrogens. Here, the important thing to know is that whenever you're using tributyl hydride, the propagating species is the tin radical. So our mechanism will look something like this. I'm skipping the initiation step, but the first propagation step is then the abstraction of hydrogen from the tin hydrogen bond. Turns out that's a relatively weak bond compared to everything else, so that's what happens. Like so. That gets us to the tin radical plus the initiator byproduct. That can then react with our halogenated alkane here. So that gets us to our tin radical and, of course, the initiator byproduct. The tin radical can then abstract the bromine from our cyclohexyl bromide here. That can take place because the tin bromine bond is actually pretty strong. So that turns out to be about 132 kilocalories per mole. And so this is a favorable process right here. Once we're at this stage, just recalling that our propagating species needs to be remade so that it can kind of continue doing this step here. What we'll do is we'll react with the tin hydride to abstract a hydrogen. And then that gets us to our cyclohexane product, tin radical, that continues reacting and propagating. Tributyl hydride turns out to also be very useful for making carbon-carbon bonds, and this reaction is most often used to form intramolecular carbon-carbon bonds. And so you can imagine making all sorts of complicated molecules with lots of rings in them this way. The way the reaction works is a combination of the tributyl hydride reduction and also just the addition of a radical to an alkene. So what we're overall doing is we're taking an alkyl bromide here in this example. We're using the tin to abstract the bromine, turn that into a carbon radical. That carbon radical is then going to be able to react with the alkene, which will then eventually abstract another hydride from tributyl hydride. So that's a mechanism that's worth working through as a way to see if you understand what's going on here. An important thing that happens with these cyclizations is that we have a choice now, right? The radical can end up cyclizing to either this carbon, that gets us to what's shown as the major product, or it can cyclize to the outer carbon, and that gets us to what I've shown as the minor product. So a question that you should come up with right away is, well, why is there a selectivity between forming the 5-membered ring and forming the 6-membered ring? And the answer for all selectivity in all reactions is always going to be in the transition states. And what you're thinking about is, well, what's an easier transition state? And so, of course, it's not so simple to figure out exactly in all this folding business of a reaction, well, what are all the correct angles that you need when it comes to the electrophile and nucleophile orbitals? Are there all these sterics that are involved that are messing everything up? And all sorts of things like that. Turns out that there's a nice set of guidelines that are called Baldwin's rules that can help us at least determine maybe which one of these cyclizations is favored or not. The way this works is a little bit more complicated, and so you can see the supplementary video for a little bit more detail on Baldwin's rules. But in general, this is all you really need to know, which is that the exo-trig reaction is favored over an endo-trig reaction. So of course you don't know what that means yet, so let me explain that. The trig here is referring to the geometry of the atom that's being attacked. So these two atoms are trigonal planar, so that's trig. The exo refers to whether the extra electrons are pushed outside of the ring or whether they're pushed onto an atom that's inside of the ring. So let me show you that here. So if I do the exo trig process on the left here in blue, what I'm going to show is that the radical is going that way. We're forming a bond there, and then the remaining radical electron is going out, right? So that is not part of the ring. So that looks like so. If I do the endo process, then what I'm going to get is free radical kind of coming out this way, and then leaving a secondary radical behind, kind of pushing a radical into the newly formed ring. That gets me to a product that looks like so. So that's how I think about it. The endo process is pushing the extra electron or electrons into the newly formed ring, and the exo process is pushing electrons out of the newly formed ring. And so I did say electrons plural because these rules work for ionic reactions as well as these radical reactions, so these are generally good to keep in mind. All right, so that was a look at various types of free radical reactions. This really only covered radical reactions that are involving homolytic bond cleavage processes. One of the newer areas of organic chemistry now is to use electrochemistry and oxidation and reduction to generate free radicals that can then go on and react, but those are not going to be covered here.